everyone. Today we're going to be talking about titrations. So the whole point of a titration is you're trying to figure out an unknown concentration of an acid using a base or the other way around. So in this flask right here, we have the analyte, which is the thing you're analyzing. So you don't know this concentration initially. And then here's your titrant, what you're titrating with. So you're using this and you know the concentration of this very well. So the whole idea of a titration is that you can figure out the moles of acid or base because at equivalence point, the moles of acid equals the moles of base. And the formula that people use for this is molarity of the acid times the volume of the acid equals molarity of the base times volume of the base. And that's because molarity times volume gets you moles. So we get moles of acid equals moles of base. So we'll do a couple of quick applications of just this formula. First question is how much of NaOH, which is 0.040 molar, is needed to titrate 200 milliliters of 0.20 HF. I can convert this to liters, but since I'll just have both of them in milliliters, so the unit won't really matter for that. So I can just do 200 times 0.20 equals 0.040 times our volume of base, because that's what the question is asking for. So then I could solve for that in my calculator, and when I do so, I get that it's about 1,000, keeping in mind this is 1,000 milliliters because I kept 200 milliliters on the side. Another thing you could be asked to do is find the molar mass of an unknown acid. If it takes 0.30 liters of 0.10 molar of this to titrate 4 grams of it. So it looks a bit different at first, but it's the same idea. You can get moles of base because you have volume and molarity. So that's the first thing we'll do. We'll get the moles of base by multiplying those two together. And this is about 0.030. And we know that moles of base equals moles of acid at the equivalence point. And then we also have grams. So molar mass is just grams per mole. So we're just going to divide 4.0 grams per 0.030 moles. And putting this in my calculator, it's about 133 grams per mole is my molar mass. So now let's actually get to the good stuff for titrations. I'm going to go over 3 steps that you can apply to any titration problem, and it'll always get you to the right answer. So the first question type, we're going to be using this. You can stop and read the directions if you want, but this is the example we're going to be using for all of our questions. So the first question you could be asked is the initial pH. This is pretty much covered in our last video. It's a basic weak acid or weak base, depending on what you start with, calculation. If you don't understand this part for any reason, you could go back to the last video, but this shouldn't be a problem for now. Now getting to the actual titration, the first situation would be when you add a little bit of your titrant. So let's say they add 5 milliliters of NaOH. The first step you're going to do is find your new molarities. You find your new molarities using this formula, M1V1 equals M2V2, and this is from a dilution. Because in principle, what you're doing is you have a little bit of HF, and then you're adding a bit more of this solution. So now this is going to be less concentrated because there's more like water. You have like 30 milliliters of this, 20 milliliters of this, and then now there's more water, so your molarity is going to change. So you need to calculate that new molarity. M1 is just your old molarity. This is how much volume you have, and then M2 is your new molarity, and V2 is your total volume. So we're just solving for M2 or new molarity. So M1, which is our old molarity, is here, and then our volume of it is 20 milliliters. It's in the directions. And then our new total volume, which we'll divide by, is 25. The denominator should be the same, and then we did the same for OH minus to find our new molarities for each of these. So when I put this in my calculator, I believe this should be 0.08, and then I'll keep track of sig figs throughout. And then this one is 0.040. So that's your first step. You're going to find your new molarities. The second step is called the limiting reagent step. So you have a bunch of OH minus sitting around in solution. That's immediately going to get consumed by this acid. This acid's going to see the strong base and react with it right away. Forward arrow. So we have 0.080 molar of this, and we have 0.040 molar of this. We have 0 of this. We don't care about the water. Which one's going to get used up first? The OH minus will get used up first. There's less of it, so we're going to use all of it. And we're going to use it here, this side as well. And then add it to our product. So our final concentrations are going to be 0.040. This is 0, and this is 0.040. So that's your second step, your limiting reagent step. Use up the titrant that you just added. And then your last step is going to be an ice chart. So now you have new concentrations. You're going to plug that into your ice chart. 0.040. This is 0. This is 0.040 from above. and then your change minus x plus x. We're able to ignore these minus and plus x's. And then setting up our products multiplied over our reactants, we get 0.040x over 0.040 equals our Ka value because it's behaving like an acid. So these will just cancel and we get x equals Ka. So x equals our Ka, and then the pH will be the negative log of that Ka value. That Ka value from above was, I believe, 7.2 times 10 to the negative 4. So we're going to take negative log of 7.2 10 to the negative 4. Or was it 7.8? Let me check. Yeah, 7.2. So negative log of that to get our pH, and we get our pH is 3.14 with sig figs. Now note that x was equal to the Ka value. That's because we were at our half equivalence point. So a shortcut to this method is if you just reached here and you notice that your titrant is half the molarity of your thing you're titrating, that means you're at the half equivalence point. And if you're at the half equivalence point, if that molarity is half of your acid or base that you're titrating, that means you can use the formula that pH equals pKa. In other words, the pH equals the negative log of the Ka. And you'll get full credit on the AP if you just say half equivalence point negative log Ka. I would still show the first step of calculating the molarities so that you show that you know you're at the half equivalence point. The second type of problem, you'd be asked to solve the pH at the equivalence point. So again, you'd start off by solving with your new molarities. This is the same first step. I went ahead and did it here because it's just applying this formula. If you want to stop and do it yourself for practice, you definitely can. But then your next step, the limiting reagent step, is going to be a little bit different. So we're going to write in our concentrations that we figured out in the previous step. And then you'll notice they both run out at the same time. And that's by definition that at the equivalence point, your moles of acid equals your moles of base. So you might be thinking, well, how do I set up my ice chart now? You may notice that you only have F minus present. And from your last video, this is a conjugate base of HF. So this is going to undergo hydrolysis. It's going to go the other way. And the reaction that this is going to do, it's going to be an ice chart, but with hydrolysis. So the reaction it's going to do is F minus plus H2O, equilibrium error, is going to yield HF plus OH minus. So this is a hydrolysis question. You can go back to the last video if you want to practice on hydrolysis. But because we only have F minus, we can do hydrolysis. So I'm just going to go like this. This is another ice chart. Plus X plus X. So now we can do x squared over 0.067. Now be careful, this is not equal to Ka. It's behaving as a base. So from our hydrolysis video, we know that Ka times Kb equals Kw. So if we want to get Kb because it's behaving as a base, that's going to be Kw over Ka. So solving for x, I get that x equals about 9.6 times 10 to the negative 7. Now careful, when you negative log x, that's not going to be the pH, that's going to be the POH, because x is our concentration of OH minus. So negative log that to get your POH, and that's 6.02, and then 14 minus that to get our pH, because we know POH plus pH equals 14. So that means that's going to be 7.98. So that's how you get your pH at equivalence point. It's a hydrolysis problem. Our third and last type of problem for a titration is if you have excess titrant. So again, first step, I did it here. You can pause and do it yourself if you want. But we first calculate our new molarities always. And now we get to our limiting reagent step. We have 0.057 and 0.086 for our initial molarities. We don't care about water. And then now the HF actually runs out first. So the HF is now at 0. And sure, you'll form some F minus. And then this, if I could do math, is I believe 29. So you can go ahead and do this as hydrolysis and get a little bit of OH minus, but that little bit of OH minus you produce from this is going to be so small compared to this. So this number is what we're going to use. We can stop right here and say this is going to be our pH determining concentration. So we can just negative log that number we have right now, 0.029, and say this is equal to the pOH, because anything else produced by the F minus, for example, is going to be insignificant. So once we negative log that, we get our pOH of 1.54, meaning pH is just going to be 14 minus that value, which is 12.46. So those are the three types of problems you could get for a titration. So to recap your three steps, you're going to find your new molarities, you're going to use a limiting reagent chart, and then an ice chart, and then hydrolysis if you're at the equivalence point. Let's talk about titration curves for a sec. So let me go back just a sec, and we'll notice that in our first type of problem, which will probably be the most common type of problem, when you're adding just a little bit of titrant at first, you may notice that at this point in time, after we've done our limiting reagent step, we have a little bit of acid and a little bit of its conjugate base. And if you remember from the last video, if you have an acid and its conjugate base, or a base on its conjugate acid, that's a buffer solution. So notice how titrations can result in a buffer solution if you're titrating a weak acid or base. So we'll talk about that right now at the titration curves. So the last thing we'll talk about is titration curves. And what a titration curve is it maps your titration onto a graph, with your x-axis being the volume of your titrant added and your y-axis being the pH. So let's first discuss the differences when you're titrating something strong versus weak. So let's say you're titrating an acid. If it's a strong acid, it's going to obviously start lower, and that's because strong acids will have lower pHs than weak acids. Strong acids, they'll dissociate better, they're better acids, they'll be lower pH. Now, how I just talked about the buffer region, that's this right here. So with a weak acid, how it works is it starts off here, and then a little bit of OH minus gets added, so it shoots up, and then it forms the buffer. So even though you're adding more OH minus, the buffer resists that change in pH. If you want to know more about buffers, that's in the last video. But that buffer region is what resists the rise in pH. So it kind of flattens out here. Strong acids don't form buffers. So for example, if I had HI, it's a forward arrow where it forms H plus and I minus. The whole point of a buffer is it has to be in equilibrium, where if you add something to this side, then it will go to this side and balance it out, and vice versa. However, with strong acids or strong bases, it's a one-way arrow. There's no equilibrium. So a strong acid and a strong base, they don't form, neither of them can form a buffer solution. And that's why here, you don't get this like rise and then dip. It just stays low the entire time as a strong acid. And then all of a sudden, it rises very suddenly, and that's when your acid gets used up fully, and then now it's just pure OH minus getting added. The thing I should note is when you're titrating a strong acid or a strong base, the equivalence point pH will always be 7. Now with this weak acid, we calculated the pH at the equivalence point earlier, and we know that it was a bit higher than 7, and that's usual. When you're titrating a weak acid, since you have equal moles of base and acid at the equivalence point, but the base is strong and the acid is weak, that means the base is going to win out, and the pH is going to be a bit higher than 7. And vice versa, if you're titrating a weak base, you're going to start here. You'll notice this dip, this quick dip, and then it forms that buffer region where it like kind of flattens out. And then you reach your equivalence point, which is a bit lower than 7 because you have a weak base, equal moles of a weak base as a strong acid. So the strong acid is going to win and lower the pH lower than 7. And then now just pure H plus being added, so it's going to stay going down. So that's all what a titration curve is. If you want to know the volume at equivalence point, you can just find the equivalence point. It's this like kind of change in curve. And then you can just go down and see that it's like a little bit less than 30 on this graph. So that's what you need to know about titration curves. If you want to know the half equivalence point, you could take the equivalence point we found to be about 30. That means your half equivalence point will be at around 15. So it's right here. So I can get the pH of this because I know a half equivalence point, pH equals pKa. So I could say at this point in time, if I have the Ka, I could say the pH equals the pKa at this point right here. If I wanted to solve others, then I would have to do the calculations we went over above. Same thing up here, half equivalence point. Right here, that's when, here it's going to be pH equals, you could say POH equals pKb. The last type of titration curve would be for a polyprotic acid. So for a polyprotic acid like H3PO4, you got multiple H's coming off in multiple steps. So this is the first step. It's our first equivalence point is here, and our second equivalence point is here. So there's two steps. So this could possibly be like H2PO4 or something similar, or H2SO4, sorry. And then I could say that here, this is the first half equivalence point, and then it's going to be equal to pKa1. And then here's the second equivalence point, and I could say the pH here is pKa2. And then that's how a polyprotic acid would look like. So yeah, that's all you need to know about titrations. To summarize, I'll write them down real quick. Your 3 steps to solve any titration. This is your golden 3. New molarities, using your dilution formula M1V1 equals M2V2. Second step, limiting reagent chart. Third step, ice chart. And then hydrolysis if necessary, only if you're at your equivalence point. And we also talked about titration curves. So thank you for watching. Good luck on the AP. Let me know if you have any questions about this stuff. It's kind of hard.